In this lesson, we're going to try to understand what is moment and what is torque and how to solve questions related to it and how to visualize them. We're going to start from simple questions so that we can at least understand how to visualize moment and turning effect. So the first thing is that we need to understand what is moment and what the center of gravity of a system may look like. So this is the syllabus from the original A-levels 9702 syllabus code, right? So we need to understand what is center of gravity. I'm going to show you an animation for this. What is considered to be stability and how to visualize what is stability and how to understand what is the situation in which a system may become unstable. So I'm going to show you an animation for that. Okay, so let's see how the box or this object may topple over. So let's play this animation and see what happens. So first we will see that the box will be tilted for a sum of the angle. Now you can see that it is tilted at this point, right? Let's go back. So it goes back to the original position. And why is that the case? Because if we look at the moment created by the weight of the object, and this is the pivot, so this will be the perpendicular distance up to the pivot, is actually anti-clockwise. That's why it's going to fall down. And if we observe this like so we can see that if it is allowed to fall down, the box comes back again. Again, we are trying a different angle at this point, right? So again, it falls back. So let's try a different angle this time around, that if we wanted to topple over, if we wanted to forcefully be toppled over. So look at this point. So at this situation, at this particular instant, the weight vector is actually on this side of the pivot. So from the pivot up to this point, this will be the distance and this will be the force. So this one is going to topple over clockwise if allowed to do so. Now let's clear out the screen and see what happens. So if we allow this to move, it will topple over and it will settle down somewhere like this. Let's try another angle, try another different angle. So even in this situation, you can observe that as soon as the component of weight starts moving on the other side of the pivot, it will cause this to topple over. Okay, so let's let it play out. So again, this also topples over. So we understand what is the meaning of center of gravity and what role it plays in terms of application of force. So we have covered the first point of the syllabus. Now we move to the second one, which is apply and define the moment of a force. Now moment, students generally confuse this with momentum. This is not momentum, this is moment. So basically we are actually trying to do the turning effect of a force, that when applied, a force may cause rotation. So for example, if we have a rod or if we have a simple balancing rod in this situation, if we apply a force at one point, the distance from the pivot, taken from the pivot, will cause a rotation that is clockwise. In this situation at least, right? So the product of force, moment is defined as a product of force and distance. One key thing over here is that work done also has the same formula, which is F into D. Then how is it different? In the case of work done, the force and the distance covered have to be in the same direction, exactly in the same direction for that to be called work done. Over here, the force and distance need to have an angle of 90 degrees between them. They need to be applied perpendicular to each other. And the distances, all the distances are taken from the pivot. Now, this is just basic O-levels ideas. Let's move on to the other idea, that is the principle of moments, which is that the sum of all clockwise moments should be equal to the sum of anti-clockwise moments. And this will help us to solve questions. Let's say that if we have a balanced rod in equilibrium, and we have, let's say, two forces acting on it at different points on both sides. So let's say this is F1, this is F2, this is F3, and this is F4. If this is in equilibrium, then the whole moment of the scenario will be balanced. And the equation is supposed to be designed around the pivot. There will be an equal to sign. Now look at the arrows. This is trying to rotate the rod in this direction. This is also trying to rotate the rod in this direction. What students mistake is to add the forces together and then solve the question. This will be wrong because we cannot add forces. We need the sum of moments So the sum of clockwise and anti-clockwise moments are required, and moment is the product of force and distance both. So we just can't add forces together to solve the question. Okay, so this side, they're trying to rotate anti-clockwise. So now we have to add moments and we have to take their distances. So distance of each force will be taken from the pivot. So this will be taken this way. So this is, let's say, D3, and let's say this is D4. This is, let's say, D2, and this is going to be, let's say, D1. So this will be F1 multiplied by D1, then plus F2 with D2. Notice that we are adding moments. We are not adding forces alone. First, we need to multiply them. On the other side, we know that this is all clockwise, right? So this will be F3 multiplied by D3 plus F4 multiplied by D4. So this will be an equilibrium position. Now let's apply this formula in an animation and let's see what this clockwise and anti-clockwise movement and motion actually looks like. So over here we have a seesaw example, and I can see that this is the pivot of the system. And if I, let's say, pick up a mass and place it on this side, I can see that it starts to move anti-clockwise. And if I pick it up again and place it on the other side, this starts to move anti-clockwise. Sorry, clockwise, right? So basically, this is what we're trying to do, that if, let's say, we have a mass on one of the instants, let's go back. Let's say we have a mass at point 1, we have another mass at point 2. What should I place on the other side so that it becomes balanced? Let's say I start with 20 kg. I place it at 1.25, nothing happens. I place it at 1.5, it starts moving and eventually attains a balanced situation. It is now completely balanced. But how do we get this? We can't do this by hit and trial again and again, but how do we do this mathematically? So in order to do that, we're going to use the principle of moments and use that idea to make the equation for this system, and then try to place this 20 kg mass exactly where it's going to come out mathematically, right? Okay. All right, so here we can see that these both masses have caused this to move in the anti-clockwise direction. So I'm going to add their moments together. How to do that? We need forces and distances respectively. So in this question, I'm going to assume that the value of G for the whole question is, let's say, 10. It makes the questions to be easy to be solved, right? But otherwise it doesn't matter. So this is 1 meters away from the pivot, and this is 2 meters away from the pivot. Pivot is the point that actually causes the whole system to rotate, or you can say it is the point around which the whole system rotates. So I can see that there are two factors on the left hand side, which is 10 kg at 2 meters. So simply F into D plus F into D would suffice. So along the pivot, I should add an equals to sign. And on the other hand side, this is what I want to find out. But I do know that I will be choosing the 20 kg mass. So I do have an idea about the force, but I don't know where to put it, right? So ideally speaking, the forces should be weights of the system, which will make this mg multiplied by distance plus mg multiplied by distance, and over here mg multiplied by distance as well. Now since distance is common on both sides, sorry, the g is common on both sides, it will be cancelled out from the whole equation. You want to involve this, it doesn't matter. You want to eliminate this, it will still remain the same. So for the sake of understanding, let's put in the values and see what happens. So over here we have a mass of 10 kg at a distance of 2 meters. I'm talking about this first factor. Then a mass of 10 kg at a distance of 1 meters, which is being equated to a mass of 20 kg, which I don't know where to put it, right? So we solve it, we get, so this becomes 20 Newton meters, this becomes 10 Newton meters, this is being equated to 20 into D. So this becomes 30. I'm going to write this at the upper situation now. So this is 30 is equal to 20 D. Now when you find D, this comes out as 1.5 meters. So according to my idea, it should be placed at 1.5 meters. Okay, so let's now put in the 20 kg mass exactly at 1.5 and see whether it stabilizes. Now the condition for stability, you will see that these arrows on both sides will turn green eventually. I'm not removing all of this written animation that I've done on the screen. I'm just going to let it play out and see what happens. So I'm going to pick up this 20 kg mass and I'm going to place it at 1.5 and let's see what happens. So it starts to move and eventually these signs become green, which means that the stability has been attained. So this is what is actually going on about in the principle of moments. This could have been done by two factors on the other side as well. It does not matter. It is very possible that there could be another force existing at this position. It would have been involved like this, F into D as well. So no matter how many factors there are, this is how you're going to solve it, right? Okay, I'm going to clear this out. So I hope that we understand the principle of moments, how it is actually applied, and what's the visualization behind it, what's actually happening. So then we understand the term equilibrium. What is equilibrium in terms of physics and moments? So equilibrium suggests two things. There needs to be two things for a system to be in equilibrium. First, the resultant force needs to be zero. What is this resultant force? This is actually the F equals to ma thought process. This is actually talking about this one, that the object should not be moving, or if it is moving, then there should be no acceleration because of that resultant. And that the moment or all the moment of the system should be zero. Although technically the equation is that the torque should be zero, but we haven't discussed torque yet. That's why I'm skipping that right now. So simply put, what does that mean? The second condition means that there should be no rotation of the system. The rotation of a system is prohibited. If a system attains these two qualities or has these qualities, then we will say that the system is in equilibrium. That is exactly why we can use principle of moments and then eventually equate both sides. Whatever the factors are trying to rotate it anti-clockwise and whatever factor are trying to rotate it clockwise, they're exactly balanced out. They're equal to each other because there should be no rotation. Okay, so then we move on towards a pair of forces producing a torque and eventually defining torque. So what is torque? It is just a simple way to find total moment of such a system that has special qualities. What are those two qualities? The first quality is that we need to have same forces. Forces need to be same. For example, if one end is experiencing 20 newtons, the other end should also be experiencing 20 newtons. The forces need to be the same in magnitude. The second factor that it observes is that the forces should be anti-parallel. Now, what do we mean by anti-parallel? Anti-parallel means that they should be exactly opposite to each other on the object. So for example, if we have a rod in this situation, we apply a force in this direction, let's say the force is 10 newtons, then there needs to be a force on the other direction, which is anti-parallel. Anti-parallel, one of them is upwards and one of them is acting downwards. What will this do to this object? It will cause this to rotate like this. Similarly, if we had a circular object like the steering wheel of a vehicle, of a car, or a tire of a car or of a bike, if one of the forces acting in this direction, let's say 30 newtons, then there needs to be a force acting on the other hand side exactly opposite to this one, making an angle of 90 degrees with exact same magnitude. If these conditions are fulfilled, forces magnitudes are same and they are anti-parallel, which is explained over here. And over here you can see that as well, that they are making an angle of 90 degrees from both sides. If you can see such a condition, then that situation, that moment will be known as torque. Now, how do you calculate this? Now, for example, if let's say that the radius of this situation is given and the radius of this situation is also given, what would you do? How would you find out the total moment? You see, you will isolate them. So first you find out the moment of this one, and then you find out the moment of this one, and then you simply add them together. What will you get? So you'll get 30R plus 30R, which will result in 2 times 30R, right? So this will become 60R. So instead of speaking or instead of saying that this is total moment, they generally say that this is torque. Now, how do you find torque and how do you avoid this and just find torque directly? So torque says that pick any one of the forces, because we know that they are the same forces, so it wouldn't matter. So pick any one of the force and multiply that force with the distance among them, distance between them, and most definitely we're talking about the perpendicular distance that is going to exist between them. So in this case, if we observe, that is R plus R. This is first R and this is second R. So this becomes F multiplied by 2R. Now we know that F was 30. So what has happened? So 30 multiplied by 2R, we get 60R, which is again the same answer. When we were thinking about this as total moment, we got the same answer. And when we think about it as torque, we get the same answer. So torque is total moment, but the conditions are that the forces should be the same and they should be anti-parallel. They should be exerted in the opposite direction and they should have a perpendicular distance between them. If there is another example in which they are not anti-parallel, then that will not be referred as torque. We will get to that example later. Okay, so we have covered most of the ideas in this topic. We're going to go directly to the questions and discuss what is going to be equilibrium, what is torque, what is moment, and how to solve them. So let's move on to the first question. This is interesting in terms of the idea that there are multiple ways to solve it. So it asks you that there is a distance from one point to another. The length is 0.3. The total length is 0.3. Equal forces are being exerted, right? They are anti-parallel. One is left, one is towards the right. So yes, this will be creating torque of the couple. It will be creating a torque. But how do you solve this? You see, we found and we discussed that there should be perpendicular distance between them, right? So we can solve it in two ways over here. What students generally do is memorize the formula of this situation, but we're not going to do that. We need forces with 90-degree angle. So what we can do is we can make two components of this 2 Newton force, one this way and one in this way. Similarly over here, one component this way and one component this way to make a 90 degrees angle in both cases. So this is going to be 40 degrees and this is going to be 40 degrees. And we know that the moment is going to be caused by this component, not this one, the one that is exactly perpendicular with the respective distance, so that we can have an angle of 90 degrees between the force and the distance. So since we are trying to find out torque, we can choose any one of the forces and the total distance between them. So it will be F multiplied by D. So how are we going to do that? The force is actually 2 newtons and its angle and respective component, this side will become F cos of 40, right? We are thinking about this component because this is going to make an angle of 90 degrees with the distance. So this becomes F cos of 40 multiplied by distance between them, which is 0.3 given in the question. So when you solve this, your answer will come out as 0.46 Newton meters. Right, so this is going to be option C. Now let's look at another example. Let's look at another way to solve the same question. I'm going to erase this method so that we can make way for the second process, right? What if the student does not want to change the value of force? What if they want to consider the perpendicular distance between them? What will happen then? So in that case, you'll have to see that the perpendicular distance between them is actually like this one. If you choose one of the forces, okay, fine, be my guest, doesn't matter. So now we know that this is a right angle triangle, right? If you want to find out this distance and you have the total hypotenuse over here, that is 0.3 meters, we can find out that this angle will be actually a component of sine. So D is equal to 0.3 sine of 50. Now use this distance and multiply this with this value of 2, you will again get 0.46. What we have done is we have made sure that we don't take the total distance, we only take the distance with reference to the force which makes an angle of 90 degrees. So you're going to get the same answer. So there are two ways to look at the same question, give you the same answer. This is where we discuss what is going to be moment and torque and what is not going to constitute as a torque. Now for torque, I go back with the two conditions were the forces should be same, they should be anti-parallel, and they should be exactly in front of each other by making an angle of 90 degrees at least. So in this example, we can see that option B is rejected. Why? Because both of the forces are different. Plus, one of them was supposed to be anti-parallel. And even if it was anti-parallel, it would still not be moment because the force is not same, which is evident in option C. Although they're exactly opposite to each other, making an angle of 90 degrees, this is F, this is 2F, will be rejected because either this should have been 2F or either this should have been F because they need to be same. Over here, the example looks a bit tricky. Although the forces are same, right, they are exactly perpendicular distance away from their respective pivot, but this will still not qualify as torque. Why? Because we need them to be anti-parallel. Anti-parallel means this should be exactly in front of them so that there can be an angle of 90 degrees. And you can say that they are exactly 180 degrees apart. One is towards the right and one is towards the left. We can see this happening in option A. Now notice that it's not necessary that it is exactly going to cause the rotation of the circle. That is shown, it does not matter. They will make their own pivot. They will make their own pivot at the center. It does not matter. But this will eventually cause a rotation as torque because forces are same and they're in opposite direction and they have a perpendicular distance between them. So option A is the correct answer. I hope this MCQ clears out what is torque and what is not going to be counted as torque. And don't get me wrong, these options will be rotating. This will rotate in this direction, this will rotate in this direction, this will rotate over here, this will rotate over here. They will be rotating. Rotation is not the criteria for torque. Torque specifically requests you need to fulfill these two conditions, same forces and anti-parallel. Rotation alone is not going to qualify as torque. So we move on to this question, again a classical example of equilibrium, whether this object is in equilibrium or not. It asks you what is the resultant force and what is the resultant torque. Are they zero or are they not zero? You can see in terms of resultant force, which comes from F equals to ma, we can see that this object is actually experiencing two forces towards the right side. So there is a resultant force of 40 newtons towards the right side. So the resultant force is not zero. And then we observe that there is a rotation, or two forces of 30 newtons are going to cause a rotation clockwise. Are the forces same? Yes. Do they have a perpendicular distance between them? Yes, they do. So this is torque, and torque is also not equal to zero. Rather, if you wanted to find out, that would have been 30 multiplied by the distance that is d between them. So torque is also not zero. So this comes out as option D, not zero, not zero. I hope it further clarifies the torque example. Now, he wants you to figure out how much force we want to apply so that this pulley or the system actually attracts this system upwards, or it can at least carry it. Okay, so how to solve this? We can understand that at least the magnitude of forces on both sides is same, and they have a perpendicular distance between them with an angle of 90 degrees among them. So this side is actually experiencing torque. So if you don't want to visualize it as torque, it doesn't matter. You could have taken the distances up to the pivot and then added them together. You will get the same answer. So the system that is trying to stop this from falling down is this F, and the system that is trying to fall down or is trying to go downwards is this one. So if we understand, then the 900 newtons force is actually transmitted to this direction with this magnitude, and this pivot or this system is actually going to act as the moment. So there is a force in this direction and there is a counterclockwise force from F. So they are both actually equal to each other, or at least for this situation. So we're going to visualize that this F torque is trying to stop this 900 Newton from falling down. So F multiplied by 1.2, the distance between them, again you can split this, but it wouldn't make any difference, is being balanced by, or is being held back by, this force F and its perpendicular distance up to the pivot, which is 0.2. So 900 multiplied by 0.2, we get F as 150 newtons. So 150 newtons of force should be applied from both sides, otherwise this will fall down. Again, another classic example of vector components. Whenever you see these vector components, please don't hesitate making components. Now understand that this 15 and 65 will make a component in this direction, and they will make a component in this direction. This is the component responsible for creating moment and eventually causing rotation. The other component is not responsible for anything, because we have an equal and opposite component in this direction as well, so it will be cancelled out. So we need to visualize that. Okay, so this is in front of the angle. You can go watch the vector component video and see how we can do this quickly and what are the shortcuts. So in front of the angle, this becomes the sine function. So this is 15 sine of 65. This also becomes 15 sine of 65. Now it's your choice. You can choose any one of them. It doesn't matter, right? And the perpendicular distance between them, which is already given to you in the question, which is 0.4. So to find out the torque, I need any one of the forces. So let's say we choose 15 sine 65 and the perpendicular distance between them, which is going to make an angle of 90 degrees with the forces. So 15 sine 65 multiplied by 0.4. If you solve it correctly on the calculator, you will get the answer as 5.4 something. So this becomes 5.4 Newton meters. And the answer will be 5.4. Option D has been taken from the latest paper. I hope that it helps. Okay, so then this is the most common example, the bookshelf example, repeatedly asked, and the students generally do get confused how to do it and what to do about this. Okay, so he wants you to find out what is the moment about X. Now, when it says about X, it means that X will be treated as the pivot. So all distances should be taken from the pivot, which is point X. That is why he needs to mention this. Okay, so we have a shelf, and we have the tension force is 15. And what is the moment of this force about pivot X? So he's asking you about what is the moment due to this 15 newtons. Now we have to be clever about this. We understand that this is not a straightforward question. We need to make components. So there are going to be two ways to solve the question. So if I draw the grid at this position, this is going to become 60 degrees. So I have two choices. Either I can make this component and then this component for this 15 tension, or I can make this component and this component. Both ways, the answer will be exactly the same. So if I choose the 60 degrees example, then this will be 15. And since this is actually touching the angle, this will become cos. So this is 15 cos of 60. And this one is in front of the angle. So this one will become a 15 sine of 30. So this is the force component that is actually moving in the upwards direction, but is going to eventually cause the moment, right? So we have the distance from the pivot, which is given to us as 0.4. I can choose any one of them. So 15 sine 30 multiplied by 0.4 or 15 cos 60 multiplied by 0.4. You will most definitely get the same answer, and that is going to be 3 Newton meters. You can try this. You can pause the video and try this. 3 Newton meters. Okay, one problem the students generally do is, since on your calculator you will see this as 15 sine and then 30, and then you forget about adding another bracket, you just do this. You just straight away multiply 0.4 and then press equals to. This is wrong. You can't do this. You have to tell the calculator where is the angle. So put a bracket over here and put a bracket over here and then over here, so that calculator knows this will be treated as the angle, and this is actually a separate multiplication factor. So please be careful about this. Otherwise, you will get the wrong answer both times. So 3 Newton meters from both edges, from both sides. I hope that this clears out any misconceptions that we have. Then we have center of gravity, and we understand this from the animation as well, which I played at the very start of the video. This is exactly the same question that is the bookshelf question, right? It first asks you about the component of T, which is the vertical component, which is responsible for this. Now we know that the tension in the question is 30 newtons, so this is 30. Then again, it's my choice. I can choose this component that is in front of this one, or I can make a component over here with an angle of 40 degrees. It wouldn't matter. It would not change the final answer. So let's make this component. So T is 30. It's given to us is 30 newtons. So this becomes 30 cos of 40. If you were making this triangle for the tension component, like this one and like this one, so this one will become 30 sine of 50. They will give you the same answers. It wouldn't matter. Okay, so you can simply write down 30 cos of 40 and then solve this, and you will get 30 cos 40 is 22.9. The answer is 22.9, but for the sake of simplicity, I'm writing down 23 newtons. Okay. So then, principle of moments, we know that the sum of clockwise moment should be equal to sum of anti-clockwise moment, which I've just described at the very beginning. The question is taken from May, June 2013-22, one of the latest questions. Now, he asks you that taking or using principle of moments, prove that the weight of the object is 19 newtons. So what he wants you to do is that the mass of this object, or at least the weight of this object, is 19 newtons. You have to prove that. Now, how to do that? We're going to take the principle of moments. So we have one force that is in the upwards direction, and it is approximately the length of the rod is 1.2. So this is from the pivot at least 1.2 meters away. So I have 30 cos 40 multiplied by 1.2. This moment is actually in the upwards direction. Or if you extend this, this is actually in the anti-clockwise direction. But if you look at the weight of this 8.5 and this mass, these are both about this point A, which is the pivot of the system. They are both clockwise, right? So I'm going to add these two factors, and I'm going to press an equal to sign and then equate it with this factor. Okay. How much is this going to be? So this is actually mg multiplied by 1.2. This is 1.2 away from the pivot. Okay. And the other factor we have is 8.5. So this is approximately half. 1.2 half is 0.6. So that will be 8.5 multiplied by 0. Now, how do I know that I have to half this? Because at some place in this question, it will mention you that this is A uniform rod. If this is a uniform rod, then its weight will be at the exact center. So if this is 1.2, then this will be 0.6 meters. Okay. So let's make this equation. So we are being opposed by this tensions component, and we are holding back this mass, and we're holding back this mass as well. So let's make that equation. This is going to look something like this. We have 8.5 multiplied by 0.6, the mass of the rod, plus the weight that is hanging on the other side, which is mg, which is of course the weight because we need the force, multiplied by 1.2 because that is how far away it is from the ledge, equals to our component, which was t cos of 40, multiplied by 1.2. Now notice that this t is actually 30, which is given to you in the question over here. Okay, so over here we find out that the weight, or W, is actually equal to 18.73, which is rounded up to 90 newtons, and hence we have shown what the examiner wants us to show, that is going to be 90 newtons. We have shown that. Then he asks us to determine the mass m, which is going to be very simple. We have W equals to mg. W is 19, mass is not known, g is 9.81, and then you can simply find mass and write down over here. I hope that this has helped you. This is the end of the lesson.